Hey guys, it is John here. What you're about to watch is a call I recently did in my SAT Skool community Mission 1400 Plus, which you can see a image for here on math word problems. In this call, I go over all of the major types of word problems you're going to see in the math section of the SAT, plus a brief overview of how to solve each one and a couple of examples on each. If you want to know why you should trust me, I personally scored a 1550 super score on the SAT myself. I also currently own the largest online SAT Skool community in the world. The call is pretty good, and if you want to attend one of these in person yourself, you can just do so with the link in the description to join Mission 1400 Plus. Just join this community, you'll have access to all of the calls. We even have a free trial going on right now. So I'll see you guys in there, but this is the call.
Honestly, I didn't really want to do this call because I kind of do hate SAT math board problems. These are definitely my least favorite kinds of problems in all of SAT math. But unfortunately, they do show up and you do have to know how to get through them. So in this call, I'm going to be going over all the major types of word problems you're going to see in the SAT math section and basically how to do every single one, a lot of them heavily involving Desmos. First, let me just say what a word problem really is. Like, in case you're not familiar, I mean something like this, like something where it's a math problem, but involves a lot of stuff that's not just straight math. So that's what I mean when I say an SAT math word problem. Whenever you start at the problem, the first thing you should do is figure out what the goal is for the problem. For a problem like this, it says, which choice is the value of L? For that problem, that would be the goal. For this problem, it says, write the equation to find out how many pens she buys if she buys 8 notebooks. So the number of pens would be the goal there. This one says, what is the value of X? So for that one, the goal would be finding what the value of X is. So when I say this word goal, all I really am referring to is figuring out what the problem is asking for, so you don't just waste a bunch of time and don't really do anything. Second, though, much more importantly, is you should, after that, write down the necessary information for the problem. So one big issue with these is when you start an SAT math word problem, there's so much stuff that's giving to you, so confusing what's happening. It's not like one problem, like, let me see if I can find an example of an easier problem. This we can see here, it's pretty clear exactly what is going on. We just say A is 50% of B is 30% of C. It's just like that, and C is equal to 200. Not really much confusion here as for what's going on. Similarly, if we have a question like, like this right triangle's length of 6 and 8, what's the length of the hypotenuse? It's pretty clear. We just have to write a right triangle and draw the things there, and that's all we have to do. For this one here, sine x degrees, it's pretty clear. It's just asking, what is the cosine of 9d minus x? So all those are pretty clear. Meanwhile, if we look at a problem like this down here, it's giving you all this other information. And yes, it isn't too unbelievably complicated, but you can see here it's a lot more confusing than if they just laid out a couple of equations. So that is how it works there. So whenever you start a problem like this, the first thing you should do is figure out the goal and then figure out what information is giving you. And you can actually just write this down either on paper, or if you want to, you can also just use Desmos. If you don't do this step, it kind of is like you're getting this like huge mass of information. It's just way too confusing to decipher on its own a lot of the time. And even if you can, it's just going to be a lot more confusing than if you do this. It's like you're taking this massive information and you're trying to simplify it down into just like a straight line. Like taking this whole big thing is making it to one straight line. I will be honest, I don't always do the second step of gathering the information first, just because a lot of times I just kind of want to save time and not really focus on it. But I would say if you are struggling with these problems and you want to improve, this is definitely what you should be doing. And I'm going to give an example throughout this call of me doing it on every single one. Okay, first type of word problem that you'll see on the SAT is linear word problems. This is pretty simple, but the way to think about all of these, and this will apply to this one and then all the other ones we'll talk about as well, is in terms of a function. Basically, almost everything in math works like this. You have some kind of input you're putting in there, and then you're getting some kind of output. So for example, maybe this could be like the amount of employees a business has. So maybe they have when they have one employee, maybe they're making like $2,000. Then let's say if they add another employee, maybe now they're making like $2,400. Maybe if they add a third employee, now they're going to get up to $2,800. So you can see here, the input would be the thing we're putting in, the thing that we can control, and then the output would be the result of that thing. I guess another good example could just be the amount of time you spend studying for the SAT. If, let's say you study for 1 hour a day, maybe you won't really get that high result. Maybe you'll only get like 1,000. If you study for 2 hours a day, maybe you'll get a high result, like 1,200. If you study for 3 hours a day, maybe that'll bring you up to like 1,400. So same kind of thing, input and getting some kind of output. And you could put these kinds of input and outputs onto a graph. So like for this here, I could have this down here be like 1, 2, 3, and it can be something basically along the lines of like increasing like that. So we have 1, and let's say this is equivalent to 2,000. 2, equivalent to 2,400. 3, equivalent to 2,800. So you can write it out on a line like this. And it won't always just be a straight line like I'm drawing here, but it can always be shown in some kind of graphical format as well. So that should make this make a lot more sense. A linear word problem that just involves linear functions would be something where you have y equals mx plus b. In this situation, y is the total amount. For like this example here, y is literally the, I guess this would be the amount of money they're making or the SAT scores that they're getting. So that is the result. M is the amount that's increasing or decreasing by. So for this one, with the SAT scores, we can see here with every additional hour per day, it increases by 200. It goes from 1,000 to 1,200, which is 200 the first time, and then 1,200 to 1,400, which would be 200 again. So that would be the rate here, and it's always put before the x. And speaking of which, the x is the input. So similar to as I showed over here, x here would be the number of hours. It can be 1, 2, 3, 4, 5, 6. And then finally, the last thing you have here is the start value. This is the first thing that you get given. So for example, here, if we put a number, like let's say you studied not at all for this. Let's say you studied 0 hours. Maybe in that situation, you get like an 800 on the SAT. So that's like that's what the start would be. That would be if you literally don't do anything at all, if you don't add anything to it, what you're going to still end up getting. For the business thing here, I mean, yeah, if you have 0 employees, obviously you're going to be making $0 because there's nobody to make it. I guess unless you use AI. A water tank holds 12 gallons and is draining at a constant rate of 1.5 gallons per minute. After how many minutes will the tank contain 3 gallons? Okay, so we're trying to see here the amount of minutes where it only has 3 gallons left. That is the goal that we're looking for here. Now for the information, I guess I'll just write here. So it starts at 12 gallons. That must be the beginning. That's the thing it says at the start. And it's draining at a constant rate of 1.5 gallons per minute. So I guess I could say 1.5, I guess G to M. So I can say minus 1.5. And after how many minutes will a tank contain only 3? Okay, so we're looking for where it's going to be only 3 gallons left. So you can see here, though this was really confusing when we started out, this makes it make a lot more sense because now I'm just like writing out all the different information we have here. So now all I'd have to do is write out a function for this. So y equals mx plus b, we know it's going to be something like this because it's saying something and it's just changing at a constant rate. Whenever that happens, it's always is this y equals mx plus b example. So I could just write here y is equal to, I guess, be negative 1.5 x plus 12. We can just check each of these numbers in case any of them doesn't make sense. Negative 1.5, that would be the rate, which would be the amount that's changing, which is correct. It's changed by negative 1.5 every single minute. X would be the thing we're putting in. So that's basically the amount of minutes. So if we only have 1 minute, it's only going to create negative 1.5. If we have 2 minutes, it'd be 2 times negative 1.5. So that makes sense. More minutes equals more drainage. And then start, yes, it would also make sense because it is starting at 12 gallons. That's the beginning amount here. Now it's just asking here, after what point would it contain only 3 gallons? You may be able to just think about this logically, but in case you're not, I can just go ahead and put this into Desmos. If we're looking for 3 gallons, it would be 3 in place of y because that would be the result. And then we could say here, negative 1.5 x plus 12. We can see here that it would have to be 6. So basically there would be 6 minutes that would have to pass to get us to only 3. So honestly, pretty simple for that first one. So this one is a little bit more complicated than the one before, but we can still solve it overall pretty easily. So let me say the goal here would be how much money it's going to have if it has 10 employees. So if we have 10 employees in the business, how much money is it going to be generated from that? Okay, so that was the goal. Now onto the information. So it has 4 employees, and when it has 4, it's making $2,000. So pretty simple there. That is the amount it's generating. After getting 2 more employees, so basically 6 now, it would be making $2,500. And then saying how much we'll be making if it has 10 employees. So it would be the same function shown up here, but the issue is we don't really know a lot of the key information. We don't really know what the start would be. Like it doesn't say how much it's starting with ever at all. We don't really know how much it is. I guess we basically know how much it's increasing, but it's kind of confusing because we add 2 instead of just 1. So we don't really have a clear rate either. And then for the inputs, I guess we technically have that. But yeah, a lot of the other stuff is not that clear. So I would suggest if you see it like this, an example like this, where it doesn't give you as much information, to instead solve it by using Desmos regression with a table. So I have a full explanation on this in the Desmos course in this community. But in case you are not familiar, basically all I have to do is just write the word table and just put in these exact things. So I say 4, 2,000, and then 6, 2,500. And then I can just go ahead and basically back solve to get this exact equation, this y equals mx plus b. So I can click here and say linear regression. And oh yeah, okay. Yeah, it just looks like a straight line because it is such big numbers. But yes, it is actually a slanted line. So yeah, we're getting here, it would be 250x plus 1000. That is the linear equation here. So pretty simple. All we have to do left is saying how much we'll make if it has 10 employees. So I could just go in here and put 10 for the number. So we do that. And yeah, it's saying $3,500. So that is the amount it'll make once it finally gets to 10. But now let's move on to linear standard form word problems. So this is not really that often. It typically appears as a system of equations instead. So this is really where we're going to be seeing most of this. But it could theoretically just appear as one. What a standard form linear equation looks like is ax plus by equals c. Basically, what's happening here is that a represents some kind of value, x represents some kind of input, same thing for b and y, and then finally we have c, which is the total amount. So a good example of what this could be referring to is something like the prices of stuff. So when I say value, that often could also mean price. So it could say maybe we have bread that costs $2 each. So I say 2x because that's $2 bread. And let's say we have milk that costs $4 each. So we could say 4 times y. And then we just have that being equal to c. So the x represents the amount of bread, y represents the amount of milk, and then c is the total amount, and this is the price of everything. So it almost always really appears as price. Like, yeah, I think these two examples that I have here, we'll see more of them here. But yeah, I think they all deal with price. So it's like, yeah, typically that's what's going to happen. But yeah, if I was to give another example, I could say here's something like, if it costs $60 for, I don't know, maybe a video game, and then it costs $30 for a controller, then this whole price would be this. And then this would represent, the X would represent the video game, and then the Y would represent the controller. Oh, so this all probably makes a lot of sense. So a student buys notebooks for $3 each and pens for $2 each, spending exactly 36. If X is the notebooks and Y is the pens, write the equation to find how many pens she buys 8 notebooks. Okay, so the goal here would be, I guess we basically have two goals. First, we have to write the equation, and then we have to find how many pens she would buy in this exact situation. So those two things would be the goal here. For the information, it's saying notebooks for $3 each. So I guess I'll say N for 3, and then pens for $2 each. So P for that. And it says the total ends up being $36. So I would say this. Now it gives us more information if X is the notebooks and Y is the pens. I'll just go ahead and just like replace these, basically X and Y. So for the equation, ax plus by equals c, same kind of thing. We have two different scenarios, one with value, one with the amount. So I would just go here and write, I guess it's 3 times x plus 2 times y, just matching these up. And that would equal, I guess it'd have to be equal 36, basically. So you might be able to see here as well, like if I was just looking at this and trying to purely write based off this wording, this may have been at least slightly more complicated than it was here. Here, I just literally just match stuff up. So it becomes so much easier once you actually write down the information. So yeah, we have this equation here, 3x plus 2y equals 36. And it's finding here how many pens if she buys 8 different notebooks. So I guess I kind of got rid of it, but yeah, the notebooks are represented by the x. So it has to be 3 times x, or 3 times 8. So it would be something then like this. So 3 times 8 plus 2y is equal to 36. So pretty simple Desmos stuff yet again. All I would have to do at this point is just go in here into Desmos and just write this exact thing. So 3 times 8 plus 2 times y is equal to 36. And we just see here where it intersects. So yeah, 6. So in this situation, we would just know that y would have to be 6. She must have bought at least 6 pens. Now, if you're familiar with the Desmos course, you know that I also can recommend another way of solving these, which is just by using regression without tables. So I can put this there and then that. Easier way, we just get the exact same thing without as much having to look at the graph. So just another way you can do that. Okay, but none of this really matters on its own for most of these problems. It really matters for the system of equations. So you can probably guess what's going on here. It's pretty much the same thing, standard form stuff, but now we just also add in the amount of items. So items plus items equals total items, and value plus value equals total value. So this was going to look like something like x plus y is equal to some amount. And then we have something like value plus value. So it might be like 2x plus 3y is equal to another amount. Just to think logically here for a second, think about what each of these is saying. X and Y are both just the amounts of the items. So that we have X amount of pens, that's some amount of pens. Same thing for Y. So for this, it would just be saying the amount of items. Yeah, I guess that's why I say total items there. Amount of items. Meanwhile, this one is saying 2 times x. So basically the price times each x, and then the price times y. So that would basically just be the total price. So that is a way you can typically think about this. Okay, moving on to this one. Smoothie shop, small smoothies, $4 each, large for $6. They sold 75 smoothies and collected $3.90. And then just gives us some information about the things. So we're trying to find what the value of L is, which would be the number of large smoothies. For the information here, we have basically just, I guess it's pretty simple, like small smoothies. So S would be $4 each. And then we have large, I'll say like that, would be $6 each. Total ends up being 75 for the amount, and then a $3.90 for the amount of money they got. So yeah, pretty simple stuff there. Really not too much more. So using this exact thing, we have x plus y equals the amount, and this equals the price. Just replace x and y with s and l. So we basically have s plus l would be equal to 75. And then we have here the price as well. So 4s plus 6l is equal to 390. So yeah, pretty simple stuff there. And then all we would do from this point on is we just put this exact stuff into Desmos. So if you want to do it the simple way, you are going to have to replace S and L with X and Y. So I would instead have to say something here like X plus Y is equal to 75. And then 4X plus 6Y is equal to 390. So something like that. And then we can just see here where they intersect, which we'll see is here. So it asks us for the choice of the value of L. So I think if we match this up here, you can see y would be L. So the y value here would be 45. So therefore, we go for 45 for the answer. If you want to do the slightly more complicated way, but the way that makes it a little bit easier for keeping track of everything, you can put it in regression without a table. So that would look like S plus L, and then we'd say, just 4S plus 6L. And a bracket, and then we say, 75, 390. Same kind of stuff here. We see L would have to be equal to 45. So if you want to save some work later on, you can do that. Another thing pretty much going to be the exact same as the one before. A theater sold a total of 70 tickets for a show. Adult 12, student cost 8. Number collected was 760, and then gives us some information there as well. So 70 tickets for a show, so I can just say 70 there. Adult ticket cost 12, so I guess I can just say, I'll just go ahead and say 12A. Just make it a little bit easier. Student ticket costs 8. And then 760. So really pretty simple here. 12A plus 8S is equal to, that'd be the price, so it'd be 760. And then we have here A plus S would be equal to 70. I'll just solve it the simpler way there. So I'll just say something like 12A plus 8S, and then A plus S, and then tilde 760, 70. Pretty simple stuff. And then value of X. So I guess they actually made it unnecessarily confusing themselves. So X would be the adults, so A would be 50. Oh yes, 50 would be the answer. Okay, so really simple stuff there. Like after you do a few of these, it just becomes very, very easy to figure out what is going on here. So really not too much more that I have to say for a lot of this stuff. What it does get a little bit more confusing is these next 4 types. First, quadratic word problems. So a quadratic function looks a little bit more like this. You have this curve, and it's either like this, or it could be like that. It's something N or U-shaped. And you always know it's a quadratic because it has a format like this. Something times that squared plus that something times something plus something. So it's always going to look like this. And think about what this could be saying. So I mentioned before the whole thing with the inputs and outputs. If this is an input and that's an output, what could this be referring to? What's an example of something that it could be saying? Yeah, that actually is a pretty good example. Like, if you sleep way too little, if the input is sleep and you do way too little, then it's going to be pretty low. And then if it's way too much, then that may also end up causing problems. It may either hurt your brain, or you also just might sleep too much that you miss the test. So it would be also pretty low. So that's a good example. And there's really not too many examples, honestly, with this kind. Well, there are a lot of examples, but not really too many easy to think of. One very common one that is on the SAT is something like some kind of specific thing that is definitely right, that's not too little, not too much, would fall into this category. So it could be something, stuff like that, like anything involving medicine, probably, like if you don't do something too much, or if you do something too much, if you take too little of a medicine, if you take too much of a medicine, obviously it's going to be that kind of stuff. On the SAT, they often do stuff like maybe throwing a ball in the air, which obviously isn't that really exciting. Pretty obvious here. This kind of does just look like a ball thrown in the air, but that's what they often do. So here is another example, though. A theme park has a water jet with a parabolic path. So this is the thing. It's the estimated height in meters of a drop of water 2 seconds after its launch. It's asking here, what is the vertex of the graph? What would it be showing, basically? So for the goal here, it's asking here what the vertex means. So that's the goal. And for the information, it's really not too much here, but we just have this function and it's the estimated height. Okay, so pretty easy what we have here. So it's going to be something like maybe, yeah, pretty much exactly like what I showed above. It's going to be something like this. It's asking what would the vertex, so the top point of this drop of water reaches an estimated maximum. Okay, well, okay, just to answer that question, first of all, it probably would be the maximum height of the thing. It would be the highest amount that this water can get. So if the water is going in the air, the highest amount it reaches before it finally just comes back down. So it's going to be something involving the maximum height. So if we look at the choices now, we see here maximum height is in this one and that one. So it can't be minimum, definitely not minimum, has to be maximum. So then we just have to figure out here which one logically makes sense. I guess honestly, this one here, we could graph it in Desmos just to make sure I could put this exact thing in Desmos just to see. But I think honestly, actually, okay, I guess I probably should put it in Desmos because yeah, this one. So it would be something here like y equals negative 4x squared plus 14.4x plus 3. Okay, so you're saying here 1.8 and then 15.96. So yeah, maximum would be the 15.96 or this one. Yeah, must be D. Maximum of 15.96 and 1.8. Okay. Pretty simple stuff there. All right, here's an example of a ball being thrown. So it's thrown upward and height is this. After how many seconds does the ball hit the ground? So we're just seeing here how many seconds until it hits the ground. Not really too much other information. Yeah, pretty much just simple here. So I'll just go ahead and write it in. So you say y is equal to negative 16x squared plus 48x. I'm just replacing t with x in case it wasn't already obvious. So it's saying here, how many seconds does the ball hit the ground? So that would just have to be, yeah, 3 basically. After 3 seconds, the ball hits the ground. Exponential stuff, you probably kind of get the idea at this point. We have this equation now, and this is basically for anything that has a very big increase as time goes on. So this could be something like, I guess maybe something like a stock. Like if you invest money in a stock, it may start out really slow, maybe growing very, very slowly. But then if you wait enough time, eventually you get to the point where it's just going very, very high and very, very fast. If you really look at this at a very high time frame, eventually gets to the point where it's going like this. So it just gets very, very fast, very quickly after some time goes on. Another way to think about this is that this is basically just the equivalent of multiplying something by a number again and again. So if I take like 4 and multiply it by 2, we have 8, 2 again, 16, 32. And then very quickly we start getting numbers that are just like extremely high. So yeah, for now we've already gone to like 2048. Now we're pretty quickly going to be getting to that. So that would be an example of exponential growth in action. It could also be exponential decay, of course. So we could just say here 4 times negative or 0.5. So yeah, getting much smaller, much smaller, much smaller. So for these, to write the equation, the total would be y again. The starting amount would be a. The amount of increase or decrease would be b. And then x would be the number of time periods. So with the stock example, if we put in like $1,000 start out, this would just be $1,000. And then however much it's increasing would be b. And then if this is like 10 years, we would just say 10. So an example could be this. Bacterial culture starts with 500 cells increased by 8% each hour. Which expression models the population after t hours, and what is the population after 3 hours? So for the goal here, it is asking, give us the equation and then also give us what is the population after 3 hours have passed. So for information here, 500 cells and then increased by 8%. So yeah, I guess I can write that down. 500 C to begin with, and then 8% going up. So using this formula from before, we could just say here y is equal to 500 because that would be the starting amount, so a 500. Then we multiply that by, I guess, 8% each hour. What that must mean is 1.08. Whenever it's getting bigger, we have to put 1 at the beginning of it to make sure that shows. And then we just finally put x. So that would be the equation here. And then it says after 3 hours, so I would just put here 3. So 621, 9. So basically 630 would be the answer here. Another example, investment of $2,000 grows at an annual rate of 5% compound yearly. Write the equation for the thing, and then after 10 years. So pretty much the same thing here. So we're finding the final value again and the equation, and the information here is it starts at 2K, and then it's growing at 5%. What I would just do there, times 1.05, and that would go, x. Oh, why did I put the 1.08? Yeah, you always just have to put 1 in whenever it's getting bigger. So for this one, the money is getting bigger, you're getting more money, you're not losing money, thankfully, in this example. And for this one, the bacteria is getting bigger, we have to get more bacteria and more bacteria. So it would have to be a 1 at the beginning. Yeah, if it gets smaller, you just put 0 instead. So this one would be getting much, much lower. Yeah, I can also show this as well to make it make a little more sense. So you see here, it starts really high, and then it just gets really, really low very, very fast. And then if we play this one, it gets very, very high, very, very fast. Yeah, so stuff like that. So yeah, that's how we're doing here. So yeah, I guess that would be the thing. So yeah, I can just put in here 10. So the answer would be like 3257. So after 10 years, it would only have 3257. Yeah, I mean, I guess actually it's pretty low, but I mean, this is what happens with 5% interest. Inequality word problems. This one pretty much just is another version of what we've already done. The only difference is that instead of being equal to something, it's going to be greater than or less than. So if you think about what we've already shown here, for like an example, like let's say this one, okay, yes. So this one is the one where you have the water and it's going down, so it's like emptying a tank. So we're saying here, y is equal to negative 1.5x plus 12. So basically, after each additional minute, it drops negative 1.5, or 1.5 basically. It drops that amount. And it has to have an equal sign there because it's exactly that amount. If we have the tank of water, and we wait 1 minute, we know it's for sure going to be, I guess, what would that be? Negative 1.5. It's definitely going to be 10.5. It's got to be that amount. No chance of it being more than that, no chance of it being less than that. The laws of physics say it must be 10.5. Similar for this one, we know that they're going to definitely have to have $3,500 after they have this amount of people. It just must be the case. That's the exact number. Inequalities, as you can guess, is where you don't have an exact number. It's more like you're just saying it must be maybe less than this amount, greater than this amount, at most. So all these different things. And I have this example here of all the different situations it could show. So you don't have to memorize all these. Most of these should make a decent amount of sense. But with the example before, let's say that with the water in this thing, we are just guessing how much is going to be left in it. So we know it's going to be at most 10.5. So this is the very highest amount it could be. It could be 9, it could be 8, it could be 7, but it definitely cannot be 11 because that'd be more than that. So that'd be against the rules. So at most 10.5. So instead, what I'd have to do, so saying here the total amount must be less than this. And I have to put X in there. So yeah, less than that. So however much it must be less than that. We could also say it must be at least 10.5. So it could be 10.5 or it could be greater. It could be 11, it could be 12, it could be 13. In that case, we do equal to or greater than the number. So you can also just see visually here, like it's saying here, anything greater than this line counts. Anything greater than that counts. With the one before, it said anything less than the line counts. So you can see here, it could be, it could be 9, it could be 10, it could be whatever. This one, it can be anything that's greater than. So when you start viewing it a bit more like that, it becomes a little bit easier to understand some of these different things. So if it says at least, it's saying here it must be greater than or equal to the thing. Like it must be at least that amount or it could be greater. At most, it must be at most that amount or it could be less. More than makes sense, just more than. Less than is less than. No fewer than, no more than. Minimum, maximum. So some of these are a little bit more confusing, but really most of them will make sense as you do problems. And I'll give one example right here. This one looks really hard, but it's actually not too bad. So a theater sells adult tickets and student tickets for a school play. Adult tickets cost 18 each and student tickets cost 12 each. The theater wants to sell at least 150 total tickets and earn at least 2,400 in ticket revenue. Number of student tickets sold must be no more than 60% of the total tickets sold. So a bunch of stuff here. And the number, at least 20 student tickets must be sold. And so X is the number of adult tickets and Y is the number of students. Which system of inequalities models the thing? Okay, so we're trying to see, the goal is pretty easy here. We're just trying to see which combination fixes the thing. Now we just have to write down the information. This is, you can probably see here, this is where writing down the information really, really does help because there's way too much stuff going on here. So adult tickets, 18 each. So I put 18A. And then student tickets, 12 each. So 12S. They want at least 150 total tickets. So 150. And they say at least. So if we go back to our example there, at least must be greater than or equal to. Okay, it's kind of weird because I put it on the opposite side. So basically what we're saying here is that the total amount must be greater than or equal to 150. So something like that. So basically we're saying here, I guess it would be A plus S. Okay, I guess I'm kind of solving the problem here as well. But the total amount of tickets must be that. So A plus S, this is representing each the amount. So that's why it works. Then it says here that it must be at least 2,400 in ticket revenue. So at least again, so again like that. So we have to do this inequality and then 2,400. Okay, and then it's price again. We're dealing with price. So we have to do the thing where it's added together. So 18A plus 12S. Okay, so that is most of the stuff. The final thing is probably the most difficult thing, or I guess the second last thing is the most difficult thing. It says that the number of student tickets sold must be no more than 60% of the total tickets sold. So you're looking here, no more than, less than, or equal to. So looks kind of confusing, but basically what they're saying is S, so the number of student tickets, no more than, so less than or equal to, 60% of the total tickets sold. So basically 0.6 times the total tickets sold, which would just be A plus S. Okay, makes sense. But you can see here, we don't really have anything in here that looks like, just to work ahead a bit, I don't see that there's going to be one exactly like that. So we had to put in a bit more work in this problem just to make it work. So S, if I just was to do some distribution real quick, some math stuff, algebra stuff, we get here 0.6A plus 0.6 S. And then if I then do some more math, if we subtract 0.6 from both sides, we get 0.4 S must be less than or equal to 0.6 A. So hopefully this still makes sense. Like all I'm doing here is I'm doing algebra on this original thing. In fact, let me go ahead and change the colors for this one because, okay, that works. So yeah, this is basically the equation 0.4 S must be less than or equal to 0.6 A. But you can see here, we still don't have anything that looks like that. So I have to do a little bit more work, a little bit more algebra. Sometimes you have to do that in these problems, which is basically I am going to divide each by 0.4. So I'm just going to get rid of some of the extra stuff. So 0.4. And finally here, if I go ahead and do that, 0.6 divided by 0.4 gives us 1.5. Yes, that is how we're getting the 1.5. So just to make this a bit simpler, let me just erase all of this because I just did all that work. And so this is basically the new information we have. One more piece of information they gave us is that at least 20 student tickets must be sold. So at least, okay, again, that's greater than or equal to. So I can just do like that, 20. And then that is for the student tickets. So S. Last thing here, it says that the X is the number of adults. So X is A. And then Y is the number of students. So I've kind of made it just clear. So I mean, as you see, if you really write the information well, it kind of just solves the question for you all the time. So we just look at all the information we have here and just trying to see which one matches literally all the different characteristics we have. So we can just use the process of elimination, basically. Which ones we see here is, so it has to have A plus S is greater than or equal to 150. So which ones does it not have that for? Or X plus Y must be greater than or equal to 150. This one is not because that says less than or equal to. Okay, all the other ones do. So that's met. And then 18A plus 12Y, okay, X, Y basically, but 18X plus 12Y must be greater than or equal to 2400. So yeah, that's that. This one does not have, so A cannot be right. So between B and C now. So we're basically using this as a tiebreaker. So basically Y must be less than or equal to 1.5 times X. So yeah, okay, B must be the answer because that's the only one that has this. This one is not. So all this information here, did a bunch of stuff with gathering the information, used this a bunch of times, but then ultimately I get to this as being the right answer. One more type here that I'm just going to briefly talk about is percentages of word problems. And the only difference between this does not really have any kind of formula to it. All you're doing here is you're using the percentage rules to figure out what equation you can write to show the situation. So I talk all about this in the percentages section of the full math course, but yeah, that's really all you're doing. Not really too much else we have to say here. If you know the percentage rules, all this becomes pretty easy. After a 20% discount, a calculator costs $48. Where this is the original price. So 20% discount. What that basically means is that there was some original price. So let's just say P for price. And then if we I guess, honestly, just the easiest way we can say this is 80% of P. Now, as for how I got the 80%, it's because it's a 20% discount. If you think about it, if you have something that costs $100 and you take 20% off, now it is only $80. And so if we're looking at the price now, it would basically be 80%, $80, whatever, after a 20% discount. We don't care how much the discount was. We just care about what it is now. So 80% of P, and that would cost 48. So I can just use regression here, 48. So 60. 60 must be the answer. The original price must be 60 here. If I'm confused about this, I want to just make sure I can say 60 times, I guess I can say 0.8, and yep, that equals 48. So yeah, pretty simple stuff there. I'll have here's a slightly more complicated one. Laptop's price is increased by 25%. A month later, the new price is decreased by 25. The final price is $11.25. What is the original price? We're looking here again for the original price. I guess I didn't really do the goal setting here, but we didn't really need to. It's pretty simple. So this one I will. So that's the original price. That's the goal. And here's the information. So increase by 25%, first thing. Then decrease by 25%. And then what is the original price? So, I mean, if you don't really know how percentages work, you may just think, okay, wouldn't it still just be 11.25? Unfortunately, that's not really how percentages work because there's all these different things. Like when you increase it, it's different from decreasing it, basically. That's main thing. So I would do the same thing here instead. I would say basically P, and I could just say, so since we're increasing now, we can basically say 125% of P. So hopefully that still makes sense. Same kind of logic here. You're taking 25% and adding it on top. So it would be 100% originally, now 125%. And then it says decrease by 25%. So it would basically just be saying 75% of this. So I can say that. So kind of confusing, but Desmos actually surprisingly does understand this perfectly. So pretty good. And yeah, that would be 1125. So it must have started with 1200. Again, if I'm not sure if that's actually correct, I can just do here. So 1200 times, I can say 1.25, 1500, and then 1500 times 0.75. That would bring me to, yes, 1125. If you want to write this without doing the percentages, you can also just say here 1.25 P times 0.75, and that's equal to that. So yeah, pretty simple stuff there. And that is really all the major types of word problems. They do have other types. Like they can come up with other stuff on the real SAT that is not any of these things. They could just throw some random stuff together that you never have seen before, because the SAT writers are always just trying to do some kind of weird thing, some kind of new thing. You can find plenty of problems on Onico that are different from this as well. So all this different stuff. But as for the major types, these are definitely it. And many times what you'll discover is that though it might seem like a different type, it is just another way of writing, or maybe more complexity added on top of one of these types.
Hope you enjoyed this. Good luck on the SAT. Make sure to always stay Gucci.